in this example, I want to really make sure that we understand the difference between what our original function tells us and what its derivative tells us, because they do have two very different interpretations. So here we have a company's total sales in millions of dollars t months from now are given by the function s of t equals 2 square root t plus 6, and our function's derivative is s prime of t is equal to 1 over square root of t plus 6. So I'm giving you the derivative in this problem because I mostly want to focus on the interpretation of this derivative. Part A asks us to find s of 10 and s prime of 10 and interpret these results. So let's start with s of 10. If I want to find s of 10, I'm taking 10 and I'm plugging that into my original function for t. So that will look like 2 square root of 10 plus 6, and then I just want to simplify this and evaluate it. So 2 square root of 16, that's really 2 times 4, and that gives me 8. If I want to talk about what this number represents, I want to look back at, well, what did this problem tell me my function represented? This function represents a company's total sales in millions of dollars t months from now. So we plugged in t equals 10. We're really using t equals 10 here. So if I wanted to interpret what this number means, I would say 10 months from now, the total sales will be $8 million. And that's it. That's all that this is telling us here. So by our projection right here, 10 months from now, we will have $8 million in sales. Now, if I want to look at s prime of 10, this is asking me to do something different. I'm still going to be using t equals 10 here, but this time I'm plugging it into my derivative. So s prime of 10 is equal to 1 over square root of 10 plus 6, and I just want to evaluate this. So 1 over square root 16, that's 1 over 4, which we could leave that as a fraction, or if we wanted to give that as a decimal, that would be 0.25. Now, interpreting this quantity is going to be a little bit different because the derivative tells us something different. Remember that the derivative, that s prime of t, that tells us the rate of change. So it tells us the rate of change at this one specific moment in time. So we're still talking about the same time from now. We're still talking about 10 months from now. And that's how I would start this interpretation. I would say, well, 10 months from now, here, what were we measuring? What were we measuring? We were measuring the total sales. So, okay, we are still talking about total sales. So 10 months from now, the total sales are, and here's where we need to make a decision, and here's where things are going to be a little bit different. Remember, we're talking about the derivative, which describes a rate of change. When I think about rate of change, I think about there's really two possible outcomes. Either your number's going up or your number's going down. If it's not changing, then your number would stay the same. In order to determine whether this number is going up or going down, or whether our rate of change is going up or going down, I'm going to look at the sign of the derivative. Here we had a positive 0.25. So since we have a positive number, intuitively we would think that our sales are increasing, and that's certainly the case here. So if we have a positive derivative, that means our rate of change is well, positive and it's increasing. But if we had ended up with a negative result, that in that case, that would mean our total sales would be decreasing. So I think it's fairly intuitive to interpret that. We're just looking at the sign. If it's positive, our quantity is increasing. If it's negative, our quantity is decreasing. So we said the total sales are increasing by, so what was our units here? Let's see, we said 0.25 million dollars, but I also want to give a unit of time because I want to know, well, are my sales increasing by this amount every day, every hour, every week, every month, every year? All of those things would have drastically different impacts on my company. So for my unit of time, I'm just going to look back at my original problem and look at, well, what was our unit for T? We said T represented months. So our total sales are increasing by $0.25 million per month. And that's how I would interpret that derivative. So the original function simply tells us this is what the total sales are. The derivative tells us how those sales are either increasing or decreasing over time. Part B asks us to estimate the total sales after 11 and 12 months. So we want to use what we actually found in Part A to find the total sales after 11 months and after 12 months. Well, in Part A, we said that after 10 months, we're starting off with $8 million in sales. But by our interpretation of the derivative, we said those sales were increasing by $0.25 million per month. So each month, my total sales are going to go up by the $0.25 million. So if I want to find the total sales after 11 months, well, 11 months is simply 1 month after 10 months. So I'm going to take my total sales after 10 months, which was 8. And we said it was increasing by 0.25. So I'm going to add 0.25 to my 8, and I should have $8.25 million. Now note that this is not an exact value. This is just an approximation. And I'll actually show you what that approximation looks like at the end of this video. After 12 months, well, I'm just adding on one more month. So I'm still going to expect my sales to be increasing by this amount. Maybe not exactly this amount because we're a little bit farther away now. We're talking about 12 months versus 10 months, but probably close to that amount. So after 12 months, I'll just take, well, what was my approximation after 11 months? It was 8.25 and add on another $0.25 million because that's how much I would expect it to be increasing by. So here I'd end up with $8.5 million. Here's what we're really doing. If we were to graph this function, 2 square root t plus 6, if I was to sketch the graph of that function, it would look, probably something like this. And I'm going to make the increase a little bit more dramatic here. Now, we found the derivative at 10 months. That's what this number I have highlighted here represents. We found s prime of 10. Remember, we can also interpret that number as a slope. That represents the slope of the tangent line at 10. So if I were to look at t equals 10 and sketch in the tangent line, which I'll do in red right here, I would see something that looks roughly like that with a slope of 0.25. Now what we did is an approximation. So what we use is we use the slope to help us estimate the exact value. So we use the red line here to help us approximate the value of that black line. So if I was to look at, say, 11, it's not going to be that far off. We're just a little bit above where we should be, but we're relatively close. At 12, we're still a little bit close, but we have certainly gotten a little bit farther away. And this is one thing that I wanted to show you, that as you get further and further away, as our tangent line gets further and further away, as we move further and further to the right, our red tangent line is getting further and further from that black line. What that means for us is that our approximation is getting worse and worse as we get further and further away from t equals 10. So if I wanted to approximate, say, after t equals 20, something that's pretty far away from 10, this approximation would be not very effective. It just wouldn't be very good because there's such a large distance between my function and my tangent line here. So be careful when you're using this approximation. It can be incredibly useful as long as you're staying close to the t value or the x value that you evaluated your derivative at. But as you move further away, that approximation will deteriorate over time, and it will become worse and worse at predicting the actual value of the function as we move away from t equals 10 in this problem.